One of the hardest parts of mathematics is writing proofs. I remember when I first encountered proofs, most of my time was spent staring at a blank page, wondering where do I start, what can be assumed, and does this even count as a proof? If this sounds familiar, don't worry. In this video series I'm going to teach you the structure of proofs and the different kinds of proofs that exist. You will know exactly where to start, what assumptions are safe to be made, and your proofs will be airtight and beautiful. One prerequisite for writing proofs is a basic understanding of propositional logic. You need to know what conditional statements are, and it helps a lot too if you understand logical operators and how to read a truth table. This is because mathematical proof writing is, at its core, logical deduction. Now let's jump straight into an example of how proofs should be structured. The exercise is prove that the sum of two even numbers is always even. When starting proofs, you should always start by writing down the proposition or statements that you're trying to prove. This makes it immediately obvious to the reader what the rest of your proof is working towards. In this example, we can write proposition, the sum of two even numbers is always even. After the proposition or statement, we can list the definitions or axioms we're going to use in our proof. This is not always needed, but it's useful to both the reader and the writer, especially when you're first starting out and you often confuse statements which have to be proven and definitions. In this case, the definition of an even number will come in handy. Definition 1. An even number is a number that can be written as 2 times k, where k is an element in the set of integers. Now we can start the actual proof, and we started by writing it explicitly with the word proof, followed by what kind of proof we are writing. In this case, I'm writing a direct proof. Now we start the logical deduction of the proof. In the logical deduction part of the proof, each step should either 1. State an assumption, 2. Be a definition, 3. Use a definition, theorem, or result, or 4. Follow logically from the previous steps. The most common first step in the proof is stating an assumption. In this case, I will introduce two variables by stating the assumptions that we have two numbers, a and b, and that these numbers are both even. In the next step of this proof, I will use the definition of an even number to say that a can be written as a is equal to 2 times m, where m is an element in the set of integers, and b can be written as b is equal to 2 times n, where n is an element in the set of integers. Every time we introduce variables, it's important to state the domain of the variables. In the next step, let's consider the sum of these two variables. A plus b is equal to 2m plus 2n. And this can be written as 2 times m plus n. This step is following logically from the previous step. Since n plus m is an integer, because an integer plus an integer is equal to an integer, we can write a plus b is equal to 2k, where k is equal to n plus m. This step is using a theorem and following logically from the previous step. Since a plus b is equal to 2k is an even number by definition, I can conclude with this statement. This shows that a plus b is even by the definition of even numbers. You should always conclude with a statement that connects back to what you wanted to prove, and you should always remember to write QED or a box to show that your proof has ended. In this example, I've written each step on a separate line to make it easier to see how the proof is built up, step by step. However, in a formal proof, I would write it as a continuous text without these extra line breaks, and this will help the flow of the proof. Now that you've seen this example, try to write this proof on your own. Prove that the sum of two odd numbers is always even. Pause the video and really try to work it out on your own. Just remember the structure: statement, definitions, proof in logical steps, conclusion connecting back to the statement. In a few seconds, I'll reveal a solution. The proof in this case looks very similar to my example. The only real difference is now we also need a definition of odd numbers. Don't worry if you didn't get it right, or maybe you missed something like that proof box at the end. Because proofs are an art and a skill, and it takes time and practice to get good at. In the next videos in this series, I will go through each type of proof, with even more practice examples, so go check them out.